When you run a program, it lives in memory. But what does that really mean? Let's break it down. Memory in programming usually refers to RAM, random access memory. It's the temporary workspace your program uses while it's running. When you open an app, load a website, or run a Python script, the operating system allocates memory to that program. This memory is often divided into different regions, each serving a specific purpose. First, there's the stack. The stack is fast, structured, and used for static memory allocation. That means data like local variables, function parameters, and return addresses live here. The stack works in a last-in, first-out way. Every time you call a function, it adds a frame to the stack, and when the function returns, that frame gets popped off. Then there's the heap. This is used for dynamic memory allocation. When you create objects, lists, or data structures at runtime, especially ones whose size you don't know in advance, they go to the heap. You can think of the heap like an unorganized storage room. It's flexible, but accessing and managing it is slower than the stack. Languages like C and C++ require you to manually manage heap memory. You allocate memory with malloc, and free it with free. But in higher-level languages like Java, Python, or JavaScript, garbage collection handles this automatically. It detects which pieces of memory are no longer being used and frees them up to prevent memory leaks. But nothing is free. Garbage collection costs CPU cycles, and poorly managed memory can still cause leaks or fragmentation. There's also the code segment, where the compiled machine code of your program is stored, and the data segment, which stores global and static variables. Now here's something most developers overlook: memory alignment and size. Different data types take up different amounts of memory. An int might take 4 bytes, while a double takes 8. On some systems, accessing misaligned memory is slower, or can even cause crashes. That's why memory layout and padding are real concerns in performance-critical applications. Also, don't forget about caching. Modern CPUs use multiple levels of cache, L1, L2, L3, to keep recently used memory closer to the processor. Writing code that respects cache locality, for example, looping over arrays in a row major order, can dramatically improve performance. Memory management isn't just a low-level concern. Even in high-level languages, understanding how memory works helps you write faster, more efficient, and more scalable code. You'll debug memory leaks better, understand crashes like segmentation faults, and be able to reason about performance bottlenecks more clearly. So whether you're allocating arrays, writing recursive functions, or dealing with large datasets, knowing how memory works gives you superpowers as a developer. It's invisible most of the time, but behind every variable, every function call, and every object, memory is at work.